thanks again for inviting me. It's a pleasure to present my work. And today we'll talk a little bit about my research, namely KoopmanizingFlows, a framework we developed for learning stable Koopman operators through a diffeomorphic map. So what's the main motivation for this work? On the one hand, we're interested in closed form trajectory generations. This is kind of a more or less always a nice system. This kind of demonstrate trajectory is usually a stable one, which is nice. And we're looking to have a closed form expression for the trajectories, which is not really possible with conventional modeling. And on the other hand, we're interested in efficient optimal control. As we see here on the right, we have an underwater vehicle, and with neutral buoyancy, it's actually a stable system, which is again quite nice and is oftentimes underutilized by conventional control methods. In general, we can say that autonomy requires safe operation and control efficiency. So what we are interested in is trajectory generation and optimal control in closed form. And the question is there a salient solution to both of these problems at once? And there might be one, namely one based on global linearization. So to not bore you with the Koopman theory, we'll skip through it. But the global linearization we'll be doing here is based on Koopman operator theory. We can skip right through this and just tell you what part of the spectrum we are interested in. It's the discrete part. It's kind of the transient case. And for the system that we consider that will be with a globally stable fixed point, we can just focus on the discrete or point part of the spectrum without a loss of generality. And in this work, we're actually interested in learning the whole semigroup of Koopman operators. And that's why we go to the infinitesimal generator case. And here we can see the spectral decomposition of the point spectrum in that case. And if we fiddle around with some operator theoretic notation where this calligraphic V is the projection, the calligraphic G is the Koopman operator generator, and this big psi are kind of the features, eigenfunctions. In this case, we can see that this is quite reminiscent of a linear time invariant model, but one that's infinite dimensional for a observable and of interest H, and this requires then finite dimensional approximations. So that presents a practical challenge because we need to make some kind of a truncation of this representation, and usually the models of this form in the community have initial lifting where we kind of dispense with the nonlinearity of a finite dimensional ordinary differential equation and kind of put all of the nonlinearity in the initial condition. And afterwards, we can see that we have a linear evolution and a linear reconstruction, all motivated by this spectral decomposition of the point spectrum of the Koopman generator. Of course, we have a trade-off because of not being able to implement infinite dimensions. We inherently will have some approximation effects, but in practice, this has been not such a big problem because we can quite well, as we will see in this talk, approximate nonlinear systems with this representation that we developed with not overly big dimension D. So what we'll be concerning ourselves here is a globally stable system with a hyperbolic equilibrium point. And you're probably aware of many works based on DMD and EDMD, but there's been the recent paper on learning stable Koopman embeddings that showed really advantageous performance, and for us at that point, a few months ago, really was the state of the art, where the authors offered a fully data-driven approach, meaning the features, the evolution, and reconstructions have been concurrently learned. And they offered formal stability guarantees. However, their representation is somewhat different to our problem setting. Their lifting and reconstruction are both vanilla neural networks, and their learning is trajectory dependent. What our work does, that's basically predicating on diffeomorphic maps, and that's why diffeomorphically learning stable Koopman operators, is also fully data-driven. It has formal stability guarantees and is theoretically well justified, utilizes the linear reconstruction that's motivated directly by the spectral decomposition of the operator, and it's not trajectory dependent. We can just work with data pairs, and we don't need sequential data to learn this representation. So here is kind of the full problem statement that we have. A dynamical system with a globally stable hyperbolic equilibrium. And we consider learning a representation from data because the problem is usually unsupervised, as well as we might only have data for the system and no actual analytical model at hand. So we can see here that the loss predicates on predicting the infinitesimal change of our state and minimizing the reconstruction as well. But it's subject to Koopman invariance and stability through a Hurwitz condition. This is basically a condition that says that all of the eigenvalues of a matrix are on the left-hand plane. And this Koopman invariance here is kind of a very important feature that we want to have in comparison to many methods that don't really take care of it, that are mostly based on pre-assumed basis function and similar heuristics. So how do we want to go about it? Here, we generalize a little bit this. We've seen in the spectral decomposition, it's mostly, it's simplified in that what we've shown, and it has kind of one-dimensional linear ODEs in its decomposition, this eigenvalue equation of the operator, basically. But here we kind of generalize this notion through the following partial differential equation, where we define what actual Koopman invariance looks like in continuous time. And now in our problem setting, we want to satisfy this constraint. So how do we propose to go about it? What we suggest is exploiting equivalence relations. And this notion is actually not so unknown. There's been a few works considering conjugacy between a linear system and a nonlinear system. Even the work of Professor Mesic, a journal from 2019, I think, Nonlinear Dynamics, considers basically almost the same class of systems, where he talks about modified or modulated Fock spaces, where we know that, for example, monomials as observables for a linear system are closed for linear systems. And this is basically the similar idea, just without any work with Fock spaces, where we were inspired by aggregation for linear systems, where people were looking at how can we kind of find coordinates where polynomial outputs are closed under the dynamics. And they are closed basically by using monomial coordinates in a special form, which we will show here. So the idea is the previous PDE we will kind of morph into it by beginning with a linear system. So for linear systems, we know, and we show in a lemma, how Koopman invariant coordinates look like. So if we consider this linear dynamics and concatenate monomials up to a certain degree, lexicographically, we get dynamics that are linearly dependent on this A underlined. And all of magenta, or all the things in this Compton diagram that are in magenta, are the things that we actually learn. So this is just highlighted here to see what are the kind of learning parts of this structured learning approach that we consider. So here we see, okay, we know how to lift linear systems and preserve Koopman invariance. So, but we have a nonlinear system, as we can see on the left. I didn't tell you this. The top row is the state space. The bottom row is basically the tangent spaces of respective spaces. So on the left, we can see that this is kind of our actual nonlinear system, and we want to bypass this. We don't like the nonlinearity of its evolution. So what we do is we utilize this knowledge that we know how to make LTI coordinates arbitrarily many, as a matter of fact, for linear systems. And this is can be considered as a generalization of spectral equivalence, if you want to consider it this way. And what we do is we try to morph our system, or kind of basically modulate our system into a linear one. And we show in our proposition that if our nonlinear system is smoothly equivalent to a linear one through a diffeomorphism is a basically continuously differentiable map with a continuously differentiable inverse, then basically lifting this diffeomorphism through this monomial construction that we propose delivers Koopman invariant coordinates for the actual nonlinear system. And note that for the class of systems we consider, this is non-restrictive, and this is something basically that that's actually expected to hold. We can be equivalent to a linear system. So basically now with this construction, we can express quite simply through chain rule manipulation an f of x, our actual nonlinear system, through this diffeomorphism and the evolution of the latent linear system. So basically, as we can see here, our problem formulation changes. The Koopman invariant condition is fully replaced by a constraint that is of the same dimension as the actual nonlinear system, which is quite nice. What we also have as a constraint is, of course, that this underlined A matrix is Hurwitz. And the nice thing about it is this is also now of reduced dimension, because the lifted A matrix, so to speak, is linearly parametrized through this smaller A matrix and with positive coefficients, meaning that basically all we need to do is make this smaller A matrix that parameterizes the big one Hurwitz. And to kind of not have this constraint, to ease it and have it basically have the problem for this constraint unconstrained, we utilize a unconstrained parameterization of Hurwitz matrices, where we parameterize this A bar through 3 other auxiliary matrices. So all we're left now is one single constraint. We're one step away from an unconstrained problem, which we could learn with usual gradient descent methods. So what we try to do here is have a structured relaxation of smooth equivalence. So we have a diffeomorphic map that's really necessitated by the theory. And to ensure that, we utilize coupling flows, an invertible neural network. And here the smooth equivalence is kind of put in the costs as a soft constraint. So we do relax the original constraint problem. This might have been done with Lagrange multipliers, but in this case, we kind of consider a simplified scenario where this is just a soft constraint. And as mentioned, it's quite important that all of the candidate solutions, so every D that's been learned, is a diffeomorphism. And now here we have an invertible neural network that's constrained by its outer structure to be an invertible map. And these S and SI and TI maps that are highlighted are basically free form function approximators in general. And this still leads, because of the outer structure, still leads to an invertible map. But what we want is a diffeomorphism. So what we do is we'd look at what type of function should S and T be, and basically it's also a non-restrictive thing. They should be continuously differentiable function approximators. So how does this kind of visually look like? So we take an evidently non-linear system trajectories on the left, and this structure that we've shown is consistent of these coupling layers that have these properties of being invertible, and with this consideration of continuously differentiable function approximators S, I, and Ti, we kind of have a novel. It's not novel. We haven't developed this. It's called usually normalizing flows, or specifically here these are called affine coupling flows. And this is also related to the name of the framework that we've given it, Koopmanizing flows. But anyway, we see a network structure, a layered structure of sequential or compositions of diffeomorphisms. And diffeomorphisms are closed under composition, which basically this becomes kind of a network of morphing into a linear system, as we can see in this picture. And of course, we can see the architecture of each of these coupling layers. And this is basically a graphic representation of the equation shown before. And basically an output of, or an input to a layer comes in. It's split into two parts. One part is used for scaling and translation. Then it's basically the scaling is multiplied with a Hammad product to this other part that's split, and the translation is then added again to this one side, to this bottom side of the diagram. And basically, in essence, the one in the splitting, one part is basically unchanged, it's just shuffled in, and the other one is kind of translated and scaled, and they combined exit to the output and then the input of the next coupling layer. And this structure is quite nice because this is basically an outer structure that always ensures that we have diffeomorphisms with S and T maps continuously differentiable. So this leads then to our main theorem of the work. And here is also the name of the whole framework, is Koopmanizing flows, stable dynamical systems. So considering this diffeomorphisms made out of these coupling flows, and basically that are each a coupling layer in a network structure, and are defined as prescribed and highlighted before through continuous differential functions S and T, every optimization problem for learning this Koopman operator representation has a solution and yields a stable system. So this is quite nice because we might have data from just one part of the state space, and we have stability guarantees basically everywhere. So on places of the state space where we have never seen any data, we are still guaranteed to be stable. And also, even if we have a few data points or whatever, because we have a Hurwitz A and because we have a diffeomorphic map D, we always end up with a stable system. What this minimizes basically how close are we to explaining the data, but it's always a stable system, which is quite nice. It's kind of, it allows for kind of safe learning or safe optimization of our model. So what we did to evaluate our method is a quite popular data set, very often used for comparing machine learning approaches or learning approaches for stable dynamical system. And this is this LASA data set, a data set of human handwriting. It consists of 26 digits, 7 demonstrations each. And it's also kind of, it varies in length from 1.9 to 8.7 seconds, which is kind of a considerable predictive horizon, if I may say. And it also breaks some of our assumptions because it's stochastic. But we still did it to just look at how the efficiency of our method is. So the black dots that we see on these pictures is the training data. The red lines is our reproduction. The green star is the equilibrium. And to also demonstrate how we converge actually asymptotically to the equilibrium, this blue extended line close to the equilibrium is basically showing an extended simulation longer than actually the time of the demonstrations, just to show how we asymptotically converge to the to the kind of final state of the demonstrations. And the gray streamlines are the approximate streamlines. So we see here on this picture that basically based on our intuition, and often also advocated by Professor Mesic, that these linear time invariant coordinates of the nonlinear dynamics contain information about the geometry. And this is a clear example, basically, with this data set, how kind of we are able to learn the geometry, because it's basically, this data set is it's a prime example of how the geometry is changed from a linear to a nonlinear system, basically just switching or representing the same dynamics just on different manifolds. And we can see that this reproduction of the trajectories that we have is actually quite well, and as mentioned, it's for a long period of time, and we also don't care about trajectories, as we basically are able to learn the whole semigroup of Koopman operators, because we work in the infinitesimal case. So as mentioned, we have a state-of-the-art method in related work, so we wanted to compare ourselves to their method. As already mentioned, they also have stability guarantees, but they are trajectory dependent, whereas we are not, and they use two vanilla neural networks for lifting and reconstruction, which is out to be more flexible, and it's not really theoretically backed, as we've seen that the Koopman operator allows for linear mode decomposition. So basically, in some sense, we have a harder task on our hands to ensure that the actual state lies in the span of the features, which the related work actually doesn't need to ensure that the state lies in the span of the features, as they return to the original state space in a nonlinear way. So what we did, we compared the two on 3 different metrics. In the middle, we have a standard RMSE metric based on the trajectories of the 2 methods. And here we can see that we have a clear advantage, but where it's more pronounced, and again, in accordance to our intuition, are the 2 metrics to the left and right. To the left, dynamic time warping distance. This is a method that's irrespective of the velocity of a curve. It's kind of comparing more or less kind of some 2 trajectories independent of time, more or less capturing actually how the curve looks like and how the geometry that's captured looks like. And as well as on the right-hand side, partial curve metric, where it's also the focus is basically on the geometry. How well do we reproduce a shape, irrespective of the time dependence? And we can see that in these 2 metrics, there's a quite significant difference that's in accordance to our expectation, as we actually do have a direct way of looking for Koopman invariant coordinates that then actually capture the geometry of the state space of these trajectories that we look into. And basically, as already mentioned, this leads to superior performance by means of a theoretically well-founded structure, which is quite nice. So now we'll kind of take a little outlook in the most recent work that we've considered. So we considered the same class of autonomous dynamics, although now it doesn't need to be a Hurwitz A matrix, and with basically a linear input entry. In operator theoretical notation, we can pretty simply extend the spectral decomposition, which then, without a loss of generality, leads to the following non-autonomous linear time invariant model. And this then modifies also our learning procedure. We have also input data to consider. The prediction loss changes. And all of the other stuff actually can hold from the autonomous case, because we have just a linear input entry that we consider. What we looked at here is first the open loop prediction. We have a system that is sort of a toy example of an underwater vehicle due to this nonlinearity with the signed squared velocity. And what we look at is a 2-second prediction of 200 random initial conditions from the state space defined as in the slides. And we see that for this case, we have a 68% average RMSE reduction compared to a Taylor linearization. And on the right, we can see kind of some sample trajectories where for a very long time, basically 5 seconds, we can very well follow the nonlinear system behavior under random control inputs. So what we look after that is, okay, how can this be utilized for optimal control? And we consider optimal control with quadratic costs. And here in front of us, we have a conventional infinite time horizon optimal control problem for quadratic costs and the dynamics that we considered here. And using our Koopman operator-based model, or Koopman generator-based model to be more precise, we can rewrite this problem in the following form, where it basically becomes a LQR problem, which is quite nice as we have closed form solutions. So as said before, we found closed form solution for trajectories because every point of every trajectory is in the span of our lifted initial condition. And here we also basically find a closed form solution for optimal control. And here is also why the linear reconstruction is crucial and much more practical than the nonlinear reconstruction of related work, as we have the possibility to basically have the same cost function as before, making us comparable to the original problem. And this Q can be kind of intuitively tuned as you would do kind of position and velocity penalties, which is not really straightforward if we have nonlinear reconstruction. Now we look at control performance for an example with much more complicated damping, where we can see much bigger gains in optimal performance. So here we can see what the setup is. We sample 50 uniformly 50 initial conditions from the edges of our state space, and we can see that overall cost reduction is 15%. It doesn't seem like much, but the system is anyway very well damped. So there's basically not too much that's possible to do in that overall regard, but we can see that the variance and mean are hugely, more than a factor of 10, hugely reduced compared to a Taylor linearization. So here, as before, in blue, we have our Koopmanizing-Flows based LQR, and in red, we have the LQR based on a Taylor linearization around the equilibrium. And we can see here, because of this dissipation knowledge that we gather by Koopman representation, we are so much more efficient and deliver overall more optimal performance, because we know where our system is actually well damped and where not. So what have we seen here in this talk as a conclusion? We've seen that we're able to construct a trajectory basis. What it's meant by that is that all of the motions are in the span of the features that we have, meaning when we lift the initial condition, all of the behavior is a linear combination of the initial conditions, just like for linear systems. And we also see that we've shown there long-term valid motion models, which is quite nice. And in this kind of very geometric example, it's quite nice to see that our intuition about learning the geometry through our theoretically well-backed approach came true. On the right, we've seen the outlook to optimal control. We've seen that we have the ability to have non-local LQR design for nonlinear systems with significant optimality increase. And before concluding, I would like to thank to my graduate student Max Bayer, my undergrad student Johannes Kiermeier, my postdoctoral colleague Stefan Sosnowski, of course my supervisor Handa Hirsche, and many others from the chair that collaborated with me or always kind of gave interesting takes on this theory, helping me understand it better and kind of develop a better perspective on it. If you have, of course, if you have any questions, I'll be more than happy to answer.
Thank you, Petar, for a very interesting talk. I think we have more than enough time for some questions. So,
and I can start with some. So, very nice talk. Thank you. A couple of questions. Well, maybe a comment to start with.
Yep.
I think one of the most interesting features and something that was observed in a different context before is this point that you mentioned, which is that you can learn on part of the state space and under certain assumptions extend that, transient dynamics to the whole state space.
Yes.
So this is a particularly interesting feature of, I think, the theory itself. If you look at the paper that there are a sequence of papers on identifying systems from data using Koopman operator theory. The Wharton group, Brunton Kutz, and then others have done it. A particular one that I want to reference is the one that we did with Zlatko Drmac.
Mm-hmm.
And in that paper, it turned out that one can use data on the attractor for the Lorentz system to find the Lorentz system everywhere, right? So you just use the data from the attractor. You don't need to sample it anywhere else. And you get the right-hand side, the nonlinear right-hand side everywhere. And so what you have shown here is that using diffeomorphism, you can do this in transient dynamics as well. But I think this is restricted to the case when you have fixed points as attractors.
Yes.
So one of the questions is, how much of this could you extend to other attractors? So for example, spectral expansions you're pointing out this paper I wrote. So down here, the spectral expansions are available, and I think you could do the optimization part. You could adapt it. So any thoughts on that? So for example, if you have a limit cycle or a periodic or a quasi-periodic attractor.
So this construction that we have, of course, in this form that it is limited to fixed points that are hyperbolic. But currently we are actually looking into that direction because, as advertised by your collaborative paper with Lan, I think, this linearization in the large.
Yep.
This basically it's a beautiful paper, I think, because it backs everything that we do in some sense, because it says that you can extend the HG theorem, and you can expect that this, what we've basically done here, can be done. And it's also not limited, or the theory using diffeomorphisms is not limited to fixed points. So this kind of smooth equivalence is at least mentioned for, I believe, there for limit cycles as well. But at this stage, we haven't really, or I haven't really looked into details on how to do it, but but it will be certainly a part of future work on how basically do the same thing for a different type of attractor.
So that would be very interesting. If you'd like, let's talk offline, and
yeah,
I can suggest a couple of things.
Yeah, that would be great.
So I have a few other questions, but maybe Erwin, maybe others can ask as well, so that I don't monopolize the discussion.
Yeah, Gautam has a question.
I have a couple of questions. Firstly, in your optimization problem for the case without control, you removed the constraint on equivalence and made it into a penalty term. Do you have, have you tried fiddling around with the magnitude of the penalty and seeing how the optimization behaves as you put larger weights on it, like convert it?
You mean this smooth equivalence penalty, right?
Yeah.
Here, yeah. To be honest, we didn't fiddle around with anything. So I know it might be strange, but we kept it bare bone. We don't have any multipliers, which we could have, to your point. We could actually have it. It will probably, it might be helpful, or it will certainly try to lead to a more closer Koopman invariance. But actually, this is something that we promised ourselves to do, but we're pretty happy with no fiddling around, which is maybe due to the fact that it's really constrained from the structural standpoint. The problem is like very, very constrained. If you look at kind of this construction that we have here, our inputs are kind of constrained anyway. So it might not lead, I don't think it would lead to huge gains, but it's something we really need to look into. But yeah.
Okay, and if I can ask a follow-up question. You said that your method only depends on the dimension of the underlying nonlinear system. So have you tried to exploit this for some high dimensional system and see if you are able to beat other methods?
For example?
It's just the thought.
I mean, if we left this, or if we went with nonlinear ODEs that are of higher dimension.
Yeah.
And at this stage we didn't. But of course, this is something that that awaits us, because you see here on the right, it's a vehicle that's as 6D dynamics and 12 combined with kinematics. So that's certainly something we will be looking into.
Okay, thanks for the talk.
Yeah.
Erin, there seems to be another question.
All right.
Okay.
I'm sorry. My name is Jimmy Zhang. I'm a student from Rowan University in New Jersey. I come to this webinar and because I have a few questions to ask both Peter and Dr. Mezic. Because right now I'm doing the studies on power systems, because I'm interested in applying Koopman operators to my studies to estimate the raging attractions. But for this type of systems, I can simplify it as a control affine system. But the vector fields, that's fx, but it's time varying. So my concern is that how can I construct the Neapolitan functions using the eigenfunctions? Because right now I only found actually one papers on how to apply the Koopmans to this work. Because most papers in my field, in a power system fields, they just do the post processing of the data to analyzes the root causes for those transient instabilities. So is there any the general methods to construct the Neapolitan functions for raging attraction estimation?
There are a number of papers on there. You should particularly look at the literature, the papers that Alexander Muhoa did. I don't know if you know our stability paper in IEEE transactions.
Yes, I have that paper, doctor.
Okay,
but
and then if you look at the paper that I wrote with Milan Korda, in that one you can see some construction of eigenfunction methodologies. I don't know if you've seen that one. That's more recent.
yeah, I read that paper in 2014, I remember, but there's like a few assumptions, but I'm not sure if my system.
Yeah, so I think if you're interested, I can talk to you after the fact, but maybe this is more suitable for, you know, discussion with the speaker than with me. So
Okay.
Sorry to interrupt. I might suggest a chapter of Alexander in the book, in the Koopman book, right? There's a whole or a pretty big chunk of things related to region of attraction estimation there, right?
Yeah.
So this
there
is
is quite a bit on this that is already out there. Yeah, thank you, Petar.
Thank you. Sorry, I have one more question. So another question is that if this system, Peter, if the methods will be vulnerable to the curse of dimensionalities, because usually what I'm dealing with is a very large systems with a lot of very high dimension matrices. So in the general methods, they only use the optimizations, for example, sum of the squares to estimate the region attractions. But in this data-driven methods, will it encounter a similar problem?
For example, this construct that we use here, kind of the cornerstone is this this diffeomorphic neural network. And these networks showed or have demonstrated to work on images. And this is a high dimensional problem. So the whole problem, how it will deal with the dimensionality, I'm not so certain. The problematic thing that is inherently high dimensional is this, it will be the C matrix probably. But when it comes to this kind of hard nonlinear part with the diffeomorphism, it has shown that it can work, although maybe not this architecture, but there's a different architectures that I didn't actually mention that also can provide diffeomorphisms and are being used on images, which are naturally high dimensional.
Thank you.
I think there is no other questions, but Igor mentioned that.
There seems one hand raised.
Yeah, but that was.
Oh, it's a okay, same person. All right. I have just one more brief comment, and that's Petar. You know, you mentioned correctly that the handwriting example, which I really liked. That's a first example of that type that I've seen, and it's, I think, connected, Erwin, to kinds of things we'd like to do with soft robotics. So it's maybe will warrant some further interesting discussions on this. You mentioned, that the problem in itself is stochastic. So maybe you had, there was perhaps a disconnect between the theory and the application, but actually there is the whole theory of stochastic, Koopman operator that is out there. And the nice feature of it's that it's almost a kind of a smooth transition. So if you add stochasticity and you're asking for results in expectation, you can actually get the geometry out again, but that geometry is in expectation. That's something that's emerging now as an interesting theme, I think. And the eigenfunctions of the associated operator are again, the key objects to study. So we can have another discussion on that.
Yeah, I'll be more than open to it. Is this somewhat related? Is also Zlatko Dermac? Was there a journal with also based on stochastic Koopman operators? Or
this was with Nelly. This was with Nelly Černjerić in Rijeka and Stenka Mačešić. Yeah. So this was University of Rijeka crew. Journal of Nonlinear Science a couple of years ago. You can take a look at that as kind of a starting point. And then Matthias Warner, my current student that's actually on the call, has done a really nice paper on numerical methods. If you want to look at that. But there are also people around the world that are doing this work. For example, Hiroya Nakao in Japan has done quite a bit. Kawahara has done quite a bit. So, you know, a particular, as you might imagine, from you know, our work, our group's work, and my own works in the deterministic case, our interest is really delineating the geometry of the state space of stochastic systems using eigenfunctions. And that's kind of the general topic. And so it fits very, very nicely to what you've described. And I think there might be some, you know, interesting developments that you can provide with your methodology to further aspects of numerical implementation of these things.
Yeah, definitely. But yeah, I also agree with you with the first point about this handwriting data set. It's kind of evident that you just change the linear system basically to, or have the same dynamics as a linear system just on a manifold. You can see kind of how, you can even imagine how a linear system was morphed to reproduce this data.
Yeah, it's been really a kind of very nice story. I know you mentioned that paper with Johan Lan. There is also some papers that we have done that we actually learn diffeomorphisms on the fly to control drones,
Mm-hmm.
for example, and aggressive flight of drones. I don't know if you know that paper, but that's with the Caltech group with
yes,
Folkestad and so Joel Burdick's group down at Caltech.
Yeah.
So this is a very nice additional contribution. This layered approach looks very interesting to me.
Yeah, just one thing that I really have to note. I had a previous work before these Koopmanizing flows, where we had a similar assumption as you've mentioned it's Folkestad, or who was the, yeah, I think
Pastor.
Yeah. We have a kind of a previous work that's related to theirs. There's the same assumption, for example, that this A is known, and it's everything based on eigenfunctions. But I really need to highlight that here we can live with generalized eigenfunctions. There it's not really open to that possibility. And the one quite important thing is it might work well in practice, but we've shown in our previous work, here you can probably see it, this learning Koopman eigencomposition that's been accepted to ACC 2022. We actually compare ourselves to that method, and the results are wildly different because
I mean,
when you're not, yeah, but the thing is where one needs to be careful is the work that they've done doesn't ensure that it's a diffeomorphism. So you can understand that these results that we have here and in the previous work don't hold. This invariance doesn't hold. So this is something one needs to be careful about.
That's a fair point.
That kind of, yeah. So this is kind of,
you have actually imposed the specific constraint. Yes.
Yeah. So this means, for example, in our case, if we go back to kind of this construction that we have, through a diffeomorphism, we ensure that these are LTI coordinates of some hyperbolic stable nonlinear system.
Yeah.
The smooth equivalence just ensures that it's the right one, is the one that explains the data. And this is kind of a pretty big deal because, for example, this products of eigenfunctions that might have been done in a work that didn't take care of this don't need to be closed at all. And basically, it's certainly much more tricky, and it's not straightforward to get the solution you are looking for compared to an approach that really considers the correct hypothesis class, and that's diffeomorphisms.
So maybe two remarks on that. While smiling, one is it was entirely perhaps beyond our intuition when we were doing the original diffeomorphism work, that this will become of substantial practical significance further down the line, as you have shown, and as you mentioned, there are some prior works on this. So one of the things, these linearization theorems, for them to go from dynamical systems theory to this kind of implementation is really a beautiful thing to see. Because I certainly didn't expect it in some sense when writing theorems. The other thing that I surmised was important, but and understood that it might play a large role when I was working on it, is this Fock space issue, where the closure itself is an important aspect of it, and so this is shown in this work very, very precisely, that one cannot just throw away those kinds of constraints as to where exactly do you work, in which space do you work.
Yeah, exactly.
If you're doing sampling in the space that is not correct, it end up with a lot of problems and unstructured solutions, really. As I was pointing out literally yesterday, because I was doing a class, take a sequence of points on the board and pass a curve through them. Now, of course, in pretty much any category, you can pass an infinity of curves to them. Okay, now refine the points and say, okay, how many curves can you pass through them? Well, if you go to analytic category, then you have restricted a lot. So that's kind of the category you're talking about. If you're in continuous category, then you can pass whatever you want. It's not. It's completely open. So this whole issue of hypothesis space is actually quite deep, I think, and you have provided some really interesting solutions here for the numerical approximation. So thank you, great talk.
Yeah, thank you. And just another note on kind of what's actually a byproduct of what we do is we always get a nonlinear model as a byproduct, not the one expressed through through these reconstruction and lifted A matrix, but one that's just a diffeomorphic model.
Right.
We basically this thing that's in the smooth equivalence is also a model, just one that we don't like.
Yes,
so,
not the simplest one. Let's go.
Yes.
I agree.
Thank you, Petar, once more for your nice talk. I'm looking forward for especially this experimental part that you'll be working in future.
Yeah, I'm excited about it too.